Hi everyone, my name is Nguyen.
I'm Noah Williams, and this is our company and senior capstone project, Safety Staff.
Before we start, we'd like to thank everyone for coming today, and we appreciate your time and effort in being here, and let's get straight into our project.
So first, let's start with a little bit about us. As I said before, my name is Noah, and I'm a senior here at Grandview High School. I've taken a lot of CAD and engineering design courses, and thus have good experience using SolidWorks. I have my CSWA in additive manufacturing, and I'm an aspiring mechanical engineer with a course that's still undecided.
And I'm Ben. I am also a senior here at Grandview High School. I've completed the AP Computer Science Principal and Computer Science A classes, which gave me an introduction into Python and Java. I've also participated in the HPE and Vines coding competition, which further expanded my knowledge in Python and Java. I am an aspiring software engineer that likes to sleep a lot, and I am also undecided on my colleges.
So let's get into our advisors first. Our expert advisor with the awesome bow tie is Professor Christopher Colson from the Colorado School of Mines. He's a professor of electrical engineering, and he also has a PhD in computer science, which, as you'll see in our project, is going to be really useful. Our support advisors are my dad, Deepak Williams, who's a software engineer, my mom, Sangeetha Williams, for support, Van's dad, Nguyen, who's an electrical technician, and Van's mom, Aitai, also for support. So, the origins of our project started a few years ago when I saw a YouTube video called Ultrasonic Sound Gun by a YouTuber named Shane. I thought it was a really cool project because basically what it does is when you pull the trigger, it shoots sound in a beam. And I knew I wanted to make it one day. So when me and Van decided to collab together for this class, I tried to convince him that we should do something using ultrasonic sound. We decided to look at what are the applications of ultrasonic sound, came to the conclusion that security is the perfect space for him to use a lot of his software skills and me to use a lot of my hardware skills.
So most security systems in the market right now only surveillance what's around them. But we want to change that with our project by making the security system being able to defend itself and defend the homes. So it's going to be broken into many parts. We have the parametric speaker. It is a high frequency directional noise that will hopefully deter any intrusion or theft. And we'll have an AI detection model that will be able to detect humans, and then sign language for a password system. We're going to have an automated targeting system that will provide a full 180% or 180-degree coverage. Throughout our project, our main question is how can sound be used to deter theft? A little bit about our logo. We chose to have a well representation in the color of silver and blue to indicate a safety, an idea of safety and innovation. And whales are notorious for their ability to communicate through sound waves, so we thought we'd draw a whale swimming in sound waves.
So let's go over a little bit the system architecture of how it will work at the end. So when we paint a picture, imagine a thief named Bob is trying to break into your home at 2 a.m. while you're sleeping. What we hope to do is have an infrared camera that uses an AI detection model to detect that Bob the thief is trying to break into your house. Then we'll position the motors at Bob and shoot an ultrasonic sound wave at him that will cause Bob the thief to run away, protecting your home. On the right over there, you can see my not so great art skills, but that's what we envisioned our system looking like from the start. On the top, you can see a camera, and right below that is the speaker system.
For the timeline we have in October, we're going to order components and begin research. November, begin production of all the components. In December, we're going to complete the speaker and complete the housing. January, integration and testing of the two systems. February is continued testing. March, finalize the system. And of course, in April, to finalize the presentation and present. This timeline was really rigorous and we straightforward.
So our presentation will be split into 3 chapters. The first chapter, Van will take you through his journey working with software and developing an AI detection model. And he's going to go over how he trains the servo motors. For our second chapter, I'm going to go over the hardware and how I built the ultrasonic speaker and developed CAD housing for all our components. And finally, chapter 3 is going to be integration of our two systems. And that's where we talk about how we combine the hardware and the software sections.
So the software side, I'll be taking over now. To begin, I had to find a microcontroller or a processing unit that provided enough processing power to run the different AI models I was going to be using. And I ended up choosing the Raspberry Pi 4, and it was really compact and it had enough processing power for me to use. And it also provided a graphic interface in which I can see what my Raspberry Pi is seeing. The initial setup has a HDMI connector connecting to a monitor for graphics interface, power, and then heat for, or a fan for heat, minimization, USB for storage, a mouse, and a keyboard. I ended up going with the infrared camera because I wanted to provide a 24 hours security coverage, even at night. And infrared camera is basically just a camera that can see lights beyond the human vision. To connect the camera with the Raspberry Pi, I used the OpenCV and Pi camera imaging library to access the camera feed and show it on the Raspberry Pi. And as shown by these pictures, here is the red picture from when there's light, blue picture from when there's not, showing that the infrared does work. And I converted both images into a grayscale format using a U420 format provided by the Pi camera libraries. And then after more research, I found out that AI usually requires RGB formatted image, which is mean that there's 3 color channels. And since I had a grayscale, which is a 1 color channel, it wouldn't work with the AI detection. So I went and tried to convert my U420 format into an RGB color image. Basically here, this is the Y channel, U channel, and V channel. And the combination of the U and V channel would create a RGB color. So I had to rearrange the thousands of pixels 30 times every second into different order and assigning them different colors to be able to do so. But I found out that to be completely, really complicated and unnecessary, because I could have just passed in the red and blue image into the AI model, and that would just work just fine. So with U420 being a complete bust, I just used OpenCV to do a color conversion on the image. Before I talk about the training models that I used, I want to brief you all on the process of training models and what it's like. So just imagine a bucket of Lego blocks, all random colors, all in different orientation, but there's no structure for them. But at least we have Lego blocks and a potential to build structure. And that's like AI training, in which AI has a structure for you to build and blocks for you to build, but it doesn't know where to put them. And that's where the data comes in. And the data plays an important part because it will be able to teach the model on where to put each block and create a blueprint that will better fit the model. And the output of that is a model that can identify any targets, or like targets that you want it to target, and then from any different images. The different AI model that I've tried is the hard cascade, which is a really ineffective human detection. And so the only 4 you have to focus on are the TensorFlow Lite, which is an object detection algorithm. ULVA is also an object detection algorithm. GTM, or Google Teachable Machine, which is a data interpretation algorithm. MediaPi for detecting human landmarks. And these are some examples of the AI models. So this is MediaPi with its detection showing red dots for a hand landmark, and TensorFlow to the right with human detection. So the first model that I experienced with was the TensorFlow Lite. It provided a false detection, but it reduces my camera FPS, or frame per second, from 30 to 7, which is a drastic decrease. And so I thought the reason for that was because of the 1,000 different classifications that the TensorFlow was able to do, and that might have caused the model to be much more complicated than I wanted it to be. So I set out to train my own model in order to minimize this lag and only to target humans. And that brings us to ULVA. It is a machine learning for object detection. The requirements for this model is that I provided with images and .txt labels. I got images and .txt labels from the open image dataset V7 from Google. And this custom model, of course, is only going to detect human, creating different imaging labels. So the way that Google has their data set formatted is each image will have its own detection boxes. For example, this one has humans, cars, traffic light, and I have to loop through all those detections and find only the human detections, in which I would write them in a TXT file with its corresponding file name. First number is the classification, followed by X, Y coordinates, the width, and the height. And this process is done for every images, and I ended up with training 27,000 images. And I tried to speed up the training by integrating a GPU, but the more that I tried, it just got worse, so I just ended up using my CPU. And this process took around 600 hours per month to train. And here's a little demo. To furtherize my understanding of the model, I have some graphs to show. So this first part is the box loss, or an error in the predicted versus actual detection box. Next is COS loss, which is the classification error in the different prediction. DFL loss is the loss in data due to the lack of data. And then the thing that you want to see from these graphs is that the trend is downward, meaning that there is a downward, meaning that the error is getting less and less, meaning that the model is getting more accurate. And if you notice here, there's a little spike at the beginning. What happened there was my computer decided to update overnight for no apparent reason, and that restarted my training by like 100 hours. And so it took a little longer than I expected. But with this model, you expect me to have a pretty complete system, right? Well, that's far from the truth, because ULVA is bad, and I hated it so much, because when I tried to run the ULVA on my Raspberry Pi, it couldn't run because ULVA required a GPU to run. It's very GPU intensive. And my Raspberry Pi did not have a GPU, and it ran on like 1 frame every 4 seconds. So like 20,000% decrease from TensorFlow. And so we went back to TensorFlow, and it was much better, but it's laggy, but it will do. Moving on from the detection part, we have different motors. We decided to go with the servo motors, in which it's able to be more accurate and it's easy to use. We used two to be able to move the camera in the X and Y coordinate. Servo movement. So the way that I initialize or move the servo is by providing it with a coordinate using TensorFlow on where it should move next. And using PWM waves or pulse width modulation, I was able to move the servo to that point. Pulse width modulation is basically a switch for on and off, and for how long. But the initial issue that I had was that I was using software PWM. Software PWM was just a software that controlled the PWM waves. And it was constantly getting interrupted because I was doing other detections and other software. And so the motor would like glitches a lot, and it wasn't like really stable. And so I switched to a hardware side of PWM and uses the PISys PWM peripheral in order to separate it from the software component and providing a more accurate and stable servo. Here's a demonstration of the servo movement. And with the movement of the camera and the detection, I didn't want the system to just like shoot everybody that it sees. So I went to make a car key using radio frequency signals. And the main processing of this circuit is going to be the Adafruit M0 trinket. It's going to process incoming RF signals and send RF signals using transceiver and receivers. So basically the whole system is going to be, when the Pi detects someone, it's going to send out a RF code that will be intercepted by any nearby receiver. This receiver is going to intercept that code and send its own code back, which will unlock the system and provide you with safety from being targeted. And I also wanted to make this system more versatile, so I created a password code system in which I trained a GTM model in order to interpret data points shown. These data are collected from media pipes, as shown before. It just basically plot all my data points, and I took hundreds of pictures, and then fed into the GTM model in order to create a model that would be able to distinguish between zeros, 1, 2, and etc. And here's a little demo as well.
If I can just add to that, Van showed me his work a few weeks ago, and he had so many notes of just random nonsense, at least to me, and so many like pictures of his hand exploded with his computer. It just looked like he had gone crazy. But clearly it all worked.
Yeah, but there's like a little limitation on this. It has a 4 feet range, and the camera's going to be mounted pretty high up. So it might not be useful, but it could be useful. Also, to finish off, I wanted to optimize the system a little bit more. It's not a bright idea to run the AI model 24 hours every day, since that would require too much power and it would literally blow up my Pi. So my solution to that was to run a motion detection model that when detecting enough motion will run the AI model for a minute and then turn it off if there's no human detected. And then I'll pass you on to Noah from the hardware side.
So now that we're done with the software side, let's get into the hardware, where I'll walk you through how I went about building an ultrasonic speaker and building the CAD housing for our system. So first, let's start with a bit of the science. As I said at the beginning, I wanted to build a speaker that could shoot sound in a beam instead of spreading out and make sound normally does. So how do you narrow a sound wave? The answer is through ultrasonics. And ultrasonic sound just means it's beyond the frequency that humans can hear. And my circuit aims, as you can see in this graphic, to take an ultrasonic signal and mix it with a normal audio signal. And changing the frequency of an audio is called modulating it. And I'm going to use that term a lot later, so just keep that in mind. And as the ultrasonic wave is outputted, it'll demodulate through the air, which just means that humans will be able to hear it. And this is similar to how FM radio works, if you're familiar with that. So, what's the potential with ultrasonics? So, typically, ultrasonic sensors are used for motion detection. If you've ever been to the grocery store and you walked up to the door and it slid open for you automatically, there's a good chance that I was using an ultrasonic transducer. And how it does that is it emits an ultrasonic signal and it just bounces off and comes back to the receiver, just telling them that you're there. My system is going to be different because it's actually going to be audible at the end. And why is that useful for security specifically? The answer is because ultrasonic sound can target a specific threat and cause minimal disturbance to a range of, or just the neighborhood or whatever is around. It can also deter theft without using lethal force or causing permanent damage. Our goal is to just cause temporary annoyance or pain to deter a thief or an intruder from whatever they might be doing. So, I began with some research about circuitry. Circuitry was completely new to me starting this year and was basically a foreign language. I began with the basics, learning how a breadboard works, which is just for prototyping circuits and plugging in wires as you run. I learned the difference between series and parallel circuits, and my circuit in the end is going to use elements of both. I also researched 3 specific components: the 555 timer, which is that little spider looking thing there, an amplifier, and an ultrasonic transducer down end. I'll go into more detail about what each of those do later. I also learned how to use an oscilloscope. Our advisor, Professor Capstone, cannot stress enough how important an oscilloscope would be to my process. If you don't know, an oscilloscope is that handy little tool right there that graphs voltage over time. And that's exactly what a sound wave is. A sound wave is just a voltage over time signal. With the oscilloscope, we can take a better look at the frequency of a sound wave, and it's going to be our troubleshooting guide for anything and everything that goes wrong in the process. So we began with some basic circuit building. I built some basic circuits, just like LEDs with switches and stuff like that. Then I built an ultrasonic range finder circuit, as you can see in the bottom right. That's similar to the automatic doors, like I said earlier. Then Professor Capstone actually invited us up to Colorado School of Mines in December, and we went over our project with him. And afterwards, he invited us to a soldering activity for his college students. Through that activity, we made these really cool snowflakes that we lit up, as you can see here, and we learned how to solder, which would ultimately be really important because in the future we would be soldering elements of our circuit. So let me walk you through how this speaker circuit is supposed to work. So first we have that 555 timer, and what that's doing is taking a normal sound wave and making it ultrasonic. It's taking the frequency and just making it 40 kilohertz, which is ultrasonic frequency, or beyond the human range of hearing. Then we take that ultrasonic signal and put it into an amplifier. This amplifier takes a 5-volt sound wave and makes it 12 volts. In other words, it's just making it a lot louder. And then finally, we have ultrasonic transducers there on the far right. Those transducers are able to emit an ultrasonic sound wave because they're built to specifically vibrate at 40 kilohertz. And as that signal passes through the air, it will become audible to the human ear again. So my first attempt to build a circuit was a huge mess, as you can see. I found a schematic online, and I just tried to plug in wires, as you can see, and nothing worked. And worse than that, it was impossible to troubleshoot because I don't know if anything worked at all, and I didn't know where to start. So I knew I had to change my approach. I knew I had to test different components before integrating everything together. I decided to split my project into 3 components. First, we're looking at the audio source, then the 555 timer circuit, and finally, the transducer array. So let's start with the audio source. For the audio source, originally I wanted to use Bluetooth because I thought it would be pretty easy just pressing play on audio on my phone and having it wirelessly connect to my speaker. As it turns out, Bluetooth is pretty complicated because it requires another microcontroller that can connect, and it requires more programming. We wanted to keep our circuit as simple as possible. So after going over it with our advisor, Professor Colston, he advised us to use a 3.5 millimeter audio jack cable, as you can see from the bottom right. That'll give us a direct connection from Van's Raspberry Pi to my circuit. Additionally, for testing, we use a 1 kilohertz sound wave, which you can see here on this oscilloscope reading. That's just going to be a baseline for future readings. So then I got to work on the 555. My first attempt again was pretty messy, as you can see in the top right, and I didn't have the right capacitance value. And you'll find out soon that capacitance is very important to 555 timers. My second attempt, in the bottom right, was wired a bit better, but again, it wasn't functional. So I had to do some more learning about what the 555 timer specifically does. It turns out the 555 timer modulates or changes the frequency of the sound wave through duty cycles. Duty cycles are basically just the intervals for how long a circuit is on and for how long voltage is being supplied. And duty cycles are determined using capacitance. The capacitors ultimately determine the frequency of the circuit, and that's what determines taking it to 40 kilohertz or ultrasonic frequency. Additionally, I had to learn to be even more neat with my circuit because it would make it easy to troubleshoot anything that goes wrong. And using an oscilloscope, I could test out the different wires to make sure everything was going according to plan. So I did some more adjusting, and finally I got the circuit oscillating at 40 kilohertz. As you can see, my wiring came a long way from the first image. There's an oscilloscope reading over there, and on it says that the circuit is correctly operating at 5 volts, and I was able to take the frequency from 600 kilohertz to 40 kilohertz. And I did this by changing the capacitance to 17 nanofards. So now that the 555 circuit was done, I decided to test it using 1 ultrasonic transducer. I'll let this video show. So as you can hear, or as you can't hear, it was very quiet. But I promise you that there was a very faint buzzing sound, so I was pretty ecstatic because that meant that I had wired the 555 timer correctly, at least to some capacity. So now I have to answer the question, how do I increase the volume dramatically? So there were 3 fixes that we came to the conclusion of. First, I could further tune the 555 timer's capacitance, and by doing this, I took it from 17 nanofards to 14 nanofards. Then I could use more transducers. We decided to start with a 3x3 array, and we could change that as time went on. Finally, we decided to up the voltage. So we changed it from 12 volts to 24 volts, effectively doubling the power supply and making it louder. So then we went about soldering the ultrasonic transducers, as you can see here in the image. I'll let Van do the talking for this part, because he became pretty handy with the soldering iron throughout this year.
So the way that Noah wanted his ultrasonic wire was in parallel. So basically I just connected all the positive to positive and negative to negative wires together using a copper wire, and then going over them with some metal alloy and then soldering them for more durability. This process was really tedious and annoying, and I had to do like 3 more of them, so that wasn't fun.
So our first attempt, we decided to use a brown fur board, and we attached the transducers, as you can see, but within a day of soldering, it broke. Even though it was functional, we knew we had to move on because we needed it to not break and be stable. So we tried to unsolder it, or try to take the transducers out, but we quickly found that unsoldering a circuit is very difficult and near impossible. So the van got pretty angry and he just ripped it apart and we had to start over.
There we go.
So as you can see, throughout our second and third attempts, we moved to 2 3x3 arrays, and we got a lot of value. Even though it wasn't as loud as we would have liked, we decided to treat it as a proof of concept because it turns out that ultrasonic transducers are not the cheapest thing in the world because they go for about $1 per unit, and we just do not have enough time to keep going and enough resources because we're working on a budget still. So now that the speaker circuit was done, here's a schematic I made. On the top left, you can see the audio jack connection. Right below that is the 555 timer circuit. Right below that is the amplifier. And on the right are the ultrasonic transducers for the output. Then I got to work on the housing for both of our systems. I designed a base that was designed to hold Van's Raspberry Pi and my speaker circuit. On top, we have an opening for the motor that could hold the whole system on top. I also designed a mount, and the mount was designed to connect the motors to the camera, also to the ultrasonic transducers, effectively connecting a lot of the systems. So now we move into our third step here, integration of Van's software system and my hardware system. So here's another look at my art skills. This is what we envisioned about a month ago when we went about building the housing and all. We wanted one harmonious system. You can see the transducers up on the top with the camera in the middle, and we wanted everything to work perfectly. Unfortunately,
the reality was that there were many issues. Those mainly being that the base was too small to house both systems, and mount was also unable to connect the motors to the transducers.
So we came up with a solution. We decided to treat our project as 2 different systems, just because we had a lack of time ramping up to this presentation, and we wanted 2 functional prototypes instead of messing things up quickly. So we have Van's camera and AI detection system that has functional motor movement and functional human detection using artificial intelligence. And we have my ultrasonic speaker system that has directional sound, even though it's not quite as loud as we would want.
Here's a demonstration for both systems.
If you want a further demonstration of how that works, just come by our table later, and it's on the back. Then here's a demonstration of the ultrasonic speaker. As you can see, it's not perfectly directional, but it gets the point across, and we're treating it as a prototype or a proof of concept. So what's the future of safe and sound? We believe it starts, obviously, with integrating our 2 systems better. We believe with just a month or 2, we can definitely put our systems together in a clean and effective way. Then Van's going to continue to work on his passcode and key system to make it even more safe and accessible to the user. And finally, we think an app is the perfect next step because it could give a user 24/7 live feed of the camera's footage and alert if the speaker has had to be used at any point to make sure nothing has gone wrong. So after reflecting on this whole project, there were 3 big things I learned. I learned the value of organization, and that pertains to circuits, because I learned you have to be very organized with building circuits and electrical engineering, so you can easily troubleshoot anything and everything that goes wrong. And that's also organization with my time, because I learned that I need to give myself attainable goals and keep myself accountable. I also learned that experience is so much more helpful than research. A lot of first semester went to research for me, but I really think I should have started actually messing around with circuits and building the ultrasonic speaker earlier, because I learned a lot more just through trial and error than I ever did from just looking at things online. Finally, I learned that collaboration is frustrating at times, but ultimately rewarding. Me and Van clashed heads on a number of occasions, even from the first days, whether it was going over the company name, the company logo, and even just getting on each other's backs about our different components. But at the end of the day, our project is only what it is because both of us are so passionate about it.
And for me, I learned the importance of time management because throughout the project I have procrastinated like 80% of the time and only working for 20%. And so I feel like if I had more time, I could have finished the system more, help build the integration part, and etc. And which brings us to the next point of procrastination. I feel like sometimes it's bad, but I feel like it's also good at the same time because in a time crunch situation, you tend to think smarter and work more efficiently. And then, which brings us to puzzle solving. Throughout this project, I had to scour the web for different information and then having to piece them all together into one system.
So here's our bibliography. And first, we just want to say thank you to Professor Poston because we know for sure we would be lost in a lot of the weeds and all the problems we face, especially this semester.
And we'd like to thank our support advisor, my mom, his mom, and dad, parents, for supporting us, and of course, thanks to you all for listening today.
Yeah.
Thank you.
Any questions? Great.
Would a higher resolution camera help fix the issues with the distance?
Yeah.
Well, I know there's like existing company with like security camera, with build a infrared camera, and like actuator rotor and stuff like that. Could you all like make a collaboration with like those big company as like a motor that can attach to like open model security camera? That
I think that's definitely a possibility. If we can figure out a way to make the AI software easily accessible and the ultrasonic speaker system something that can be easily attached to an already security system, I think that's pretty feasible. JL?
So I'm just curious, how big is the AI file on your hardware? Is it like how much space does that take?
It didn't take up much space. The TensorFlow Lite is like a light version, so it's like supposed to be less accurate and less intensive than the actual. But like the YOLO VA was like a lot. It like did not run at all from my Raspberry Pi.
Have you considered using an accelerator, an AI accelerator card on your Raspberry Pi?
I don't know what that is, but if it's necessary, I'll definitely use it.
Daniel?
For like the speakers with like directionally, like how would you, do you know how you would maybe go to fix it so like it's just only right in front of you, nothing besides you saw?
Can you say that one more time?
Like how would you, because you showed in your test that like it was mostly directional, but there was still some like excess sounds from left or right.
Yeah.
Would that just be better speakers, or how would you go about fixing
I
it?
think part of it is getting better speakers, and also I think there can be a little more fine tuning with how the circuit works. Just getting it to be perfectly. I don't know how attainable like perfect ultrasonic system is, but this is the best we got for now, and we're treating it more like a prototype. Anyone else?
Go ahead.
So for the sound, like I'm kind of looking now, but like, do you think that bigger speakers are bigger than model of the design would help more with achieving that sound? Or?
So we definitely need a lot more of these ultrasonic transducers if we want the sound to actually be damaging or loud enough to travel like a good amount of range. So there are two directions we can take it. Probably just buying a lot more of these and building a better setup for all of them. In all my research, I didn't really come across other accessible ultrasonic transducers. So I think this is what we're working with for now. There's probably better technology and more well-made ones out there, but these were the cheapest ones we could find for now. So.
Are you actually planning to service like a website company?
I think
Yeah, I think that's an option.
Yeah, it's definitely an option. First we want to see if we can fully like integrate everything, get everything running pretty smoothly, and then we can kind of determine that.
Have you considered like other than just like pure sound? Have you considered maybe like say something or something like that?
Yeah, so it can actually play any noise because it's just coming through the audio jack. I was just using like a tone because I thought that was really annoying, and after I was testing, it would just ring in my ears for some time. So I thought it was pretty annoying, but it can theoretically. The quality isn't the greatest because it is ultrasonic. It's not just like a normal speaker, but in theory, it can play anything.
Yeah.
Thank you.